Hello, 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 and welcome everybody to Math for Thursday. It's December 10th. Today, welcome. We are going to be working on, that's not it, I forgot to update the title. We already did this on Tuesday. We're working on prime numbers and factor trees today. Sheesh. Off to a great start. And then now it looks all funky. There we go. All right. Whew. Whew. We're off to a rough start here. But we will persevere and rebound and have a great math day. Prime numbers and factor trees today. Sounds like a fun time. Some new stuff in here. Okay. There's what you're going to need. There's the I cans. They're down there. I did update those ahead of time. I can define a prime number as a whole number whose only factors are 1 and itself. And I can create a factor tree that shows all the prime numbers the prime factors of a composite number. So first, let's start with this idea of a prime number. And I'm actually going to move the word wall out of the way for now because I'm going to write up here. So reminder, a prime number, there we go, get rid of it fully. A prime number, we've talked about this before. We talked about it last year in 4th grade. But a prime number refers to a number. Oh, I didn't update this banner either. I'm a mess today with these banners, guys. I'm just gonna put it down there and get rid of it. Prime numbers is something we talked about last year in 4th grade, but we're going to go a little deeper into it. So just to remind, if we have our handy-dandy multiplication table right here, the only place that prime numbers are going to show up on this multiplication chart are in the ones column or the ones row, okay? Because it's the only way you can take two whole numbers and multiply them together to get that number, if it's a prime number, would be 1 times itself, because as we know, 1 times anything is that same anything, okay? So, for instance, starting small, right? 1 is neither prime nor composite, which is not prime. Okay, so we have prime or composite, because it can't be multiplied by 1 in itself because it is 1. Okay, so 0 and 1, right? They can't be prime or not prime. 0 because it isn't really a value. It's a placeholder. 2. We can do 1 times 2. Can we do any other whole numbers to get to 1 times 2? No. So 2 is going to be our first prime number. I'm going to put our prime numbers up here. Same thing with 3, right? 3 is also prime because the only way you can multiply two factors together to get 3 is 1 times 3. You couldn't do 2 times some other whole number and get 3. It'd be 2 times, what would it be, 2 times 1.5 makes 3. But we're dealing with whole numbers only here. So 3 is prime. 4. 4, 1 times 4 equals 4, but then also 2 times 2 equals 4. Okay? Even though there's only one other example, that's enough to make it composite. Okay, so here's all our primes. And we're not going to add 4 to that list because we can prove that it's not with one example. 2 times 2 equals 4. Okay, that's all the examples you need to prove that a number is composite. Okay, so if we had a number like, let's say, 40. Okay, is this number prime or composite? Can we multiply two whole numbers together to make 40 in a way additional to 1 times 40 or 40 times 1? Okay, all we need is one example to prove that it's composite. Okay, if you've got your multiplication chart in front of you, great way to figure it out. If you see 40 anywhere in the middle, anywhere other than the ones row, the ones column, or the ones row, you know you've got a composite number. And I already see it right there with 4 times 10 equals 40. So we can say that 40 is composite, okay? Otherwise known as not prime, right? There are other examples, right? Somebody said 8 times 5. Absolutely. One that's not on here but could be included, 20 times 2, okay, equals 40. So three different examples there of ways we can prove that a number is composite. Okay, what about a number like 29? Let's just go down by a few here. 29. Do we see 29 anywhere on this multiplication chart? I see 27, and then I see 30. I'm looking for numbers near 29 because that might help me. 28 to 32. 25 to 30. 24 to 30. 28 to 35. I'm not seeing it. 29 is a prime number. The only way, the only multiplication expression that will simplify to 29 would be 1 times 29, or its equivalent of 29 times 1. That would be an example of a prime number. Okay. On your exit ticket, which is going to come up on Google Classroom in just a little bit once this lesson is over, it's going to ask you to determine whether a number is prime or composite. And if it's composite, remember, all you've got to do is find one example that proves that it is composite. Okay? If you can't find any examples, then either it's prime or you've missed something. Either way, right? All you need is one example of a prime number. Okay? This prime number knowledge is going to be really important because what we're going to be working on today is what's called a factor tree and factoring out composite numbers. I'm going to pull back up the word wall again here. And down here at the bottom, as I change the title, there we go. It's going to bother me if I don't change it. Down here at the bottom, we see this definition of factor, a number that, when multiplied with another, produces a given product, right? One and itself are factors of prime numbers, and so prime numbers only have 2 factors. And what we do with factor trees is we're going to take a composite number and we're going to think about what factors. Let's take 20 to start. Thinking about what factors does 20 have? 20 is a composite number. And how can we multiply 2 numbers together to make 20? How can we multiply 2 numbers together? What 2 numbers can we multiply together to make 20? And the reason we call it a factor tree will become clear in a second. Okay? We can start with, let's see, 5 times 4. So we're going to draw our 2 lines. We're going to go 5 and 4. Okay? Now let's look at 5 and 4. Are both of these prime? Are neither of them prime? Are they both composite? Or is one prime and one composite? Okay, we look at 5. 5 is a prime number. And actually, I'm going to circle 5 so I remember that it's a prime number. 4, as we said before, is not a prime number. Okay, how do we factor out 4? Well, there's only one, as you remember. 2 times 2. And is 2 prime? 2 is prime. Okay. So what you end up with is an expression that shows all the prime numbers that multiply together to make 20. So you'd end up with 20, and it is started, you know, it's kind of looking like a Christmas tree-ish, right? We'll put a little star at the top, okay? And with bigger numbers, it will look more like a tree. 20 equals 5 times 2 times 2. Okay? And the cool thing about this factor tree is no matter how you factor out this composite number, you're always going to come up with 5 times 2 times 2 as your end product. I'll prove it to you. Instead of 5 times 4, let's use 10 times 2. Somebody else put that in the chat. So instead of 5 times 4, we're going to use 10 times 2. Now, remember, if it's prime, like 2 is, that's where the tree stops. If it's composite, like 10, the tree continues. So what two numbers multiply together to make 10? Remember, we're not using 1 times itself, because then we're going to end up in this kind of infinite loop. Okay? So what two numbers multiply together to make 10? 5 and 2. And both of these are prime, so then we end up 5 times 2 times 2. Whoa. Right? So no matter what, whether you put 5 times 4 here or 10 times 2 here, you're going to come up with 5 times 2 times 2 as your ultimate, your sort of final expression. That's got nothing but prime numbers in it. And nothing but prime numbers in it. And when you multiply them all together in any order, because it's the commutative property of multiplication, you end up with 20. Okay? Quickly, let's build a couple more prime numbers in here that might be useful. So let's see. Is 6 prime or composite? No, 6 is composite, right? 3 times 2. What about 7? 7's a prime number. Only way you can get there is 7 times 1. Let's keep going. 8, no, 8's composite, right? It's in the 2's. 2 times 4. 9, is 9 composite or prime? 3 times 3 equals 9. So 9 is composite. 10, we already went over, right? It's 5 times 2 or 2 times 5. And then what about 11? Yeah, 11's prime. Can't think of anything else that factors together to make 11. 12, we've got lots of things for 12, right? We've got 2 times 6, 4 times 3, 3 times 4, 6 times 2, lots of factors of 12, right? And then 13, I'm also going to put on here, is a prime number. Okay, so these are kind of our first 6 prime numbers here. Tough thing about prime numbers, there isn't really a pattern to it. Okay, mathematicians are still literally finding new prime numbers to this day. There are 12, 15-digit numbers that are prime. Of all those numbers below it, it's still the only way you can make a multiplication is 1 by itself. Wild. Okay, so remember these: 2, 3, 5, 7, 11, 13. I'd write them down if I were you. You've got 10 seconds to write them down. There we go. All right, let's go to the digital whiteboard. And let's look at some more factor trees here. We've got 100. 100. We're going to keep it 100 here. So thinking about what numbers, 100 is composite. Okay, you can't do a factor tree with a prime number because it's its own factor tree essentially. What two numbers can you multiply together to make 100? There are a few of them. We've got 100 equals 10 times 10. Let's do it. Okay, 100, whoops, turn my pen on here. 100 equals 10 times 10. Now, are we done? Is 10 prime or composite? Remember, if it's composite, keep going. And I see 10 is 5 times 2. So let's simplify that further. 5 times 2, 5 times 2. Okay. Are all these prime, or 5 prime and 2 prime? Yes, they are. So what you end up with is a final equation of 100 equals 5 times 2 times 5 times 2. You could put this in a different order if you wanted. You could say 5 times 5 times 2 times 2, and it would be the same thing. Is this the only factor tree we could make? No, absolutely not. Let's go with a different one. Okay, we got another one in the chat. 5 times 20 equals 100. So let's back it up and see if we come up with the same 5 times 2 times 5 times 2 when we get down to it. So we have 5 times 20. Okay? 5 is prime, so that's going to be in there. We'll circle that. 20 is composite. We just did it on the board. Okay? Let's use 4 times 5 here. Equals 20. That 5 is composite again. And we have 2 times 2 equals 4. So then we end up with, again, 5 times 5 times 2 times 2. 5 times 2 times 2 times 5, once you get down to it. Should we do a third one? Let's. How about, ooh, I see 50 times 2 in the chat as well. So let's try that one. 50 times 2. 2 is prime. So we can circle it and be done with that branch. Let's factor out 50. All right, 50 could be 10 times 5, could be 25 times 2. Let's use 10 times 5. Okay, remember, circle the primes and those branches have ended, and then factor out the composite numbers again. 10 equals 5 times 2, and they're both prime. So again, any way you slice it, you end up with 5 times 2 times 5 times 2 equals 100. Pretty fascinating stuff. Let's try 2 more real quick. Okay, 63. 63. What 2 numbers? 63 is composite. What 2 numbers multiply together to make 63? Check your multiplication chart here. Looking around, do I see things in the 60s? Aha, I see 63 here, and 63 is 9 times 7. So let's factor that out. 9 times 7. Are either of these factors prime? 9 or 7? Well, 7 is prime, so we can circle that. And that branch, is 9 prime or composite? 9 is quite composite. We've got a factor there. Remember, we've got 3 times 3. And our 3's are both prime. We've got all prime numbers now, so we can rewrite it as 63 equals 3 times 3 times 7. Or 7 times 3 times 3, or 3 times 7 times 3. Any of them work, because the factors can change order in a multiplication equation, but the product stays the same. Okay. Are there any other ways we can make 63? I think it's interesting that some people, if you've picked up on it, you could work backwards. Think about, well, if we put parentheses here, let's say, to make 9 times 7, what if we put parentheses here? and do the 3 times 7 first. What does 3 times 7 equal? And does 21 times 3 equal 63? You bet it does. So this is how kind of using factor trees can help you play around and figure out what other factor pairs might you not know, right? Okay. So let's try one more. We're almost there. 32. 32 is a fun one. Okay, go ahead and try that one on your own. What two numbers, what pair of factors would multiply together to make 32? See if either of those factors are prime or composite. If they're composite, keep factoring them out. Find two more numbers that make that smaller number, and so on and so on. And then what do you end up with? 32 is a fun one. I picked it on purpose. Take a little bit on your own while I, let's see, what should I do while I wait? Maybe I'll draw a crab on the board while you work on that. There it is. We'll give it whiskers. It's a crab. It's a cat crab. Okay. 32. Let's take a look. So we've got 8 times 4 in the chat. Let's start that. 8 times 4. And then how do we factor these ones out? Because 8 and 4 are both composite. 4 factors out to 2 times 2. Those are both prime. And then what do we do with 8? 4 times 2. And then factor it a third time. 2 times 2 equals 4 again. So then what you're left with, oh my gosh, check that out. 32 equals, let me count my 2's, make sure I got them all. 1, 2, 3, 4, 5. 2 times 2 times 2 times 2 times 2. Whoa. Or if you're familiar with exponents and multiplying a number by itself, once you get to middle school, you'll be writing 32 equals 2 to the 5th, meaning 2 times 2, 5 times. That's kind of bonus for you. You don't have to worry about that right now. I'm just putting that in your head for later so that when you go to middle school math and see exponents, you go, oh yeah, I've seen this before. Pretty cool, huh? It's just all 2's over and over and over again. There's a lot of numbers like that. See if you can figure out our doubles over and over and over again, right? Make sure you've got the right number of 2's in there. If you have too many 2's or not enough 2's, it won't be the same thing. All right. Thank you, everybody, for tuning in. Exit ticket should be up now. And I do appreciate you coming and watching this lesson. Try it on your own. If you have any questions, the office hour is opening up in about 5 minutes from when I end this stream. So do come in. I'll throw some more practice problems at you. We can do some larger factor trees if you're feeling up to it. Especially if you are feeling comfortable with your long division. It's a great way to practice long division is to find a factor tree of 2048. See what happens. right? All right, everybody. Thank you for coming. I appreciate you. We will see you soon.